Good morning. I am Krishna Kumar from Krishna's classroom with another episode of Riemann integration. And we are coming more or less to the final stage of the discussion on Riemann integration. And to connect, we briefly recall what exactly we did in our last lecture, very briefly, so that you are in with the necessary background. Now recall that we were concerned about the completeness problem. We specifically looked at 2 or 3 spaces. One was, of course, CAB, with norm infinity. This is the sup norm that you define for functions defined on the interval a to b. Of course, we have minus infinity less than a less than b less than a. Okay. Then we proved that this space is complete. Complete in the sense that all Cauchy sequences of functions in this metric space converges, or in this normal linear space converges to a function in CAB itself. That means all Cauchy sequences of continuous functions on the interval AB in the framework of sup norm and the induced metric converges to a continuous function. Okay, so that's the first thing that we looked at. Then we had CAB with another metric. Norm 1. Now, norm 1 is the metric that is induced through the integral of f, or the norm 1 was the norm introduced through the Riemann integration, namely norm f integral a to b mod . Because these two spaces are different, and in fact what you have is this one, we have straight away CAB as sets. That means there are more functions in this class. So you have got the following scenario. This is CAB with the norm 1. Now this is complete metric space, whereas this is not a complete metric space. So this is not We demonstrate it by going to the space C01 with one norm and constructing a sequence of continuous functions on the interval 0,1, which eventually converge to a discontinuous function. Okay, so the limit of, and we show that the sequence that we have chosen is a Cauchy sequence. So you actually demonstrate that there exists a Cauchy sequence of functions, of continuous functions, which in the L1 metric do not converge to a continuous function. So that was our strategy. So we have shown that this is not complete, and we worked on showed that there exists a Cauchy sequence of continuous functions in this way. Which has a limit which does not have a limit, this is what. Therefore, in general, these kind of spaces are not complete. Okay. So what we are now, you know that CAB is a very large class of functions which we usually work with, generally on integration and so on. But then quite often we have to go beyond that and even consider functions which are not necessarily continuous. Okay, so we introduced, you recall the path we followed, we introduced the concept of derivative, the concept of integration. This is Riemann integral, which is called the Riemann integral. And then we could use that to define a metric, or we characterize the Riemann integrable functions. And we denote it by RAB. So on RAB, we introduce the norm, one norm. Look at this space. Okay. Now you clearly see that every continuous function is a Riemann integrable function on the interval AB. Therefore, you have now this relation is satisfied. And you know that this is not complete, and what you anticipate is this probably RAB will be a completion of, well, just a wild guess. RAB will be a completion of CAB. So this was our expectation, so that the effort that we have taken to define or introduce the concept of integration rigorously is giving rise to a complete metric space, and one can do analysis very comfortably on complete metric spaces. Now this is one of the serious concern for analysts, because analysts do not like working on incomplete metric spaces. The reason is this: the sequences of elements in that space which can possibly converge. I mean, that's what we express by saying it's a Cauchy sequence. Would eventually get out of the space, and this is something which the analysts do not like. They want to, at least the ground should be reasonably safe to work. And once again, I think somewhere I said this example. It is dreadful to play a game of football on the deck of a ship where the deck has no, barricades. Because there is always a danger that you may chase a ball and just fall into the sea. Something like this. You may chase a convergent sequence and eventually you see that it is not there in the space. So you are likely to go away from the space. I mean, this is a sort of scenario that no analyst would like. So generally you would like to work in a complete metric space. And fortunately, one of the powerful theorems that you have always says that given a metric space, it has a completion or can be embedded in a complete metric space. So there exists always a completion for a given metric space. That's a very consoling thing. Although does not solve the problem completely, because quite often it's a very abstract way in which you realize the completion of the metric space. Naturally, you would like to ask what exactly is the manifestation of the completion of a given metric space. Because what are the objects that you take? For instance, you would like to take CAB with norm 1 and you look at the completion of this. What exactly is the nature of objects which is the completion of this? Because if you are familiar with the proof of that abstract theorem of on the existence of a completion, you will realize that it doesn't tell you much. But one of the paths on which mathematicians were very successful was in really identifying what are the manifestations of the completions of many spaces where you would like to work on. So you are at this stage, your expectation is that RAB with norm 1 is a possible candidate for the completion of this. Is it really true? Okay, so our theme that we are going to pursue here in this talk today is to show that this is not so. Okay, so we prove that this is our task. So to prove that this is not complete, it is enough to demonstrate a candidate for RAB with a possible choice of A and B, and there again a specific sequence of Riemann integrable functions on that space converging, not converging in that space. Okay. So in fact, more precisely, we prove that R 0 1 is not complete by actually picking up a Cauchy sequence of functions and then saying that it does not have a limit in the space. So that's our next task. But before that, I want to make one remark. We have seen this thing. CAB with norm infinity, CAB with norm 1. This is a larger class of functions, certainly. Okay. Now, what you want is the following. Okay, you said this is complete. Because if you choose Cauchy sequences within this class, you never get out of this class if you were to play around with this, with the metric generated by this norm. On the other hand, you were to use the same norm, this norm, then you see that this is not the case. Okay, so let me just, actually this is not more functions that you have here. So strictly speaking, I think I should possibly use the same thing with a second norm. Yeah. Okay. So it is CAB itself, but with this norm. Okay. So let me write here same thing with 1. And we show that this is not a complete space. Therefore, you might have a doubt. What happens to the sequence that we have picked up on C01? We constructed a sequence of functions C01, which is Cauchy with respect to the 1 norm, and then proved that its limit is not a continuous function. Okay? So you see that if you look at the point-wise limit of that sequence, it is a step function that you end up with a discontinuity at half, as we have constructed. Okay? So you get a discontinuous function. But how sure are you that it is, if you work in this one, it doesn't go to that? Because we have proved that it is a complete CAB with the norm infinity is a complete space. But how does this does not contradict the particular example? And in that context, we proved that the sequence of functions which are Cauchy in norm 1, the sequence of continuous functions which are Cauchy in norm 1 is not a Cauchy sequence in norm infinity. In fact, we proved the following, that norm of Fn minus F2n, this is equal to 1 and does not go to 0 as n tends to infinity. This is what we proved. So it's not a Cauchy sequence. The sequence which is Cauchy in the context of norm infinity is not, sorry, the context of norm 1 is not Cauchy in the context of norm infinity. Therefore, we were not bothered about the limit of that. Okay, right? So that is just a remark to stress the point. Okay, now let us start working on this problem. So we set up certain general notions which are required for this purpose. So this is what we intend. So the general setup that we have. So we take RAB. That is all Riemann integrable functions on the interval AB. Then we introduce the L1 matrix. So let D1 defined by integral A to B mod so one observes the following. See, we know that integral A to B does not imply f defined in T. This is a problem. What happens? Suppose you take the function which is 0 everywhere on the interval AB and except possibly at finitely many points where the function takes the value 1. So it's a discontinuous function. Nevertheless, it is a Riemann integrable function from what we have done already. Okay? And then if you look at the integral of that, since it has discontinuities on a finite set of points, otherwise it is 0 elsewhere. You see that the set of discontinuities is a null set. Therefore, it's a Riemann integrable function, alright, and the Riemann integral turns out to be equal to 0. Okay? So, this function f of x defined to be 1 at x equal to xn belonging to the interval AB and equal to 0 has integral A to B mod f 0. Okay. So even when the function is not identically equal to 0, it's possible that this integral is 0. So from this integral vanishing, you cannot conclude that f is equal to 0. So this is one point. Therefore, what we have is that d1 fg equal to 0 does not imply that is f not identity. So not necessarily we can come to this conclusion. Okay. So this is a problem. That is, we make some observations. You see that d1 fg is greater than or equal to 0. 2 d1 but not. But even when f is not equal to g, this may be 0. So the second condition for d1 to be a metric is not adequately met. Okay, so we put a mark here. And the third property is this. d1 fg, this is true for is less than or equal to d1 this is the triangular inequality. All these are satisfied, that you can verify, where of course you define dfg as defined as integral a to b okay, right? So this fails to meet the conditions for being a metric, fall short of that because of this condition. Okay, therefore you see that d1 is a pseudo-metric. That means all conditions are satisfied other than the requirement that dfg is equal to 0 if and only if f is equal to g. That if and only if part is this. If part is met, but only if part is not met. Then you say it's a pseudo when all other conditions are satisfied. Okay? So we want to, from here, we want to first construct a metric space out of it. Okay? So let us do that. Therefore, now what we do is the following. So we take our, so consider, so the second part, construction of space, this pseudo-metric. RAD. Okay, let us do that. This construction is a standard construction that we go for doing such things. Okay. So what do we do? So on RAB, so you have all Riemann. On RAB, define a relation we said that f is related to g if Gx is a null set. That means this set can be packed into a union of intervals whose total length is say 0. Okay. So once you or can be made arbitrarily small. Okay. So that is so you can find such a pattern. This is what we call a null set. And we have seen that they differ. We say that f is related to G if f and G differ only on a null set. Otherwise, they are identical. We call the definition of null set that we introduced in the earlier lecture, in one of the earlier lectures. Okay. Now, the first thing that you prove is that we show that this is an equivalence one. So we have to check three things, namely reflexivity, symmetry, and transitivity. So we check one by one. Now f is related to f. That is quite simple because the set on which f differs from itself is the empty set. Okay, and whose it is a null set automatically. So this is automatic. F is related to G implies G is related to A. So the set on which f and G differ is a null set, which is the same as the set on which G and f differ. So that's rather trivial. And the third part is f is related to G, G is related to H, f is related to H. Okay, this needs a little bit of work because you look at the sort of set. You can get the following. You take A, the set X, X, B, the set not equal to X. Then you look at the set C this is consistent with the notation that we have used. F is H is G. So we do this. Therefore, what you do? You know that this is a null set, this is a null set. Okay? And from that you have to conclude this is also a null set. And you can quickly see that C is contained in A, B, and use this fact to conclude that C is a It's some little bit of work on that. Okay. So you see that the third condition is also satisfied, which in turn tells you that R AB with the relation that you have defined. The relation that you have defined is an equivalence relation on RA. So what does it do? It induces a partition of RA. So this is an equivalence relation. Relation inducing a partition of R. Okay. So let us call this R bar AB. So the set of R the equivalence classes therefore on this one so we can further prove the following, that is integral a to b fx dx is equal to integral a to b gx dx whenever if f is available. Okay. So this is something very easy to prove because all that you need is this integral a to b mod equal to 0 This is also something that you can. Okay. Therefore, now we take R bar, the equivalence class on RAB under the metric L1 metric that we have. Okay. So we defined on RB on RP dot AB. We define this is equal to where f belongs to the class f tilde f bar and G belongs to the class G tilde G bar. Okay, then you can show that actually D bar is well defined. Okay, that means now you are having equivalence classes Suppose this is F tilde, this is the class G tilde. Then what you have is, there is an F here, there is a G here. There are so many other elements. Now you can talk about the distance between this class and this class, and that is defined as the distance between F and G in the L1 metric, and you can show that it is well defined. So D bar is well defined, and D bar F bar D bar equal to 0 if and only if F bar equal to 0. That means R D1 bar is a metric space. In fact, what one has to show is that if there is another G, there is another F bar, F tilde and G tilde such that they belong to these classes, then the distance you compute from that, from the difference between them, is going to be the same as the difference that you compute from F to G, so that you see the D bar is well defined. I mean, this is a very standard technique that one uses. Okay, you would have seen in many circumstances, like even while constructing rational numbers from fractions, you would have seen similar things happen. So this is one of the very standard practices that one uses in such constructions. And that is something that people should be very familiar with. So now what we are looking for is a metric space. Now we want to assert that under the metric D bar. If you want, you can drop this bar henceforth if you understand that it is the RAB that you have constructed and then taken the equivalence classes, etc., etc., and then complete we defined from the pseudo metric, we define a metric, and then you can, without loss of generality, you can denote this by R under D bar. Henceforth, without loss of generality, we shall designate the space of equivalence classes by with metric, not a zero metric now. Okay, henceforth we will be simply using this, by which you mean you have done all these exercises and gone from the pseudo metric notion to the metric notion, we just use the same notation. That's all. Right? Now our claim is that RAB is not, D1 is not complete. Okay, so that will be. So we by showing that it is enough to verify that this does not happen for an example, because we are making a very general statement. You show that for a particular case it doesn't work, so therefore it cannot be working for universal. And that's the argument that you have. So in this context now, we record. So this is our task. Okay, so record C alpha for contestant. So we make use of this particular very fascinating set, and it is with the purpose of constructing very powerful examples, going deep into the structure of the spaces, that we introduced, gave an introduction to C alpha. So C alpha is important. So you have a whole class of Cantor sets available, and of course you also have the C1 is the usual Cantor set. Okay, let us just recall this construction, because that is essential for understanding this particular example. So we start with this. Start with the interval. Take the middle. Now we introduce a interval. We take an interval symmetric about the midpoint half and with radius alpha by 3. What is the radius? So this is actually half minus 3. This is half plus alpha. This points. Now just to delete this. So call this A1. In fact, you call it I11 to begin with, because you need that notation. A1 equal to what is called I11. So open it. Okay. Look at the complement. The complement of that is a closed set, which is the union of two closed intervals that you can easily work out what it is. Call that V1. So you define okay. Now you observe that the following, you call the measure or length of B1 equal to 1 minus alpha by 3. That's it. Now what do you do? Take the same interval, take B1, so this together now you take the middle point, then this is the portion that you have removed, and you have B1 here, so this is your A1 and B1 is the correction. Now what one does is you go to the middle of each one of this, okay, and then remove from this a open set symmetrically placed of this point of radius alpha by 3 square. So this is the radius is alpha by 3 square. This is alpha by 3. This is alpha by 3 square. Remove that here as well as remove that here. Go for the balance of it. So this together means a union of these two. The intervals is A2, and then you get the notation right. I don't want to do notation. So what you have is that A1 equal to I11, A2 equal to, okay, right? Then what you have removed this part, you have removed this part, and so on. So you get the complement as a set B2. Okay. So you take so you call this A2, the union of these two as A2, and the remaining part you call this, the complement of that you call B2. So you have got okay. Now we take this B2 and once again go to the midpoint and remove a open set from it of radius symmetrically placed at the center with radius alpha by 3 cube. Okay. And from all these 4 intervals, you remove this middle alpha by 3 cube portion, I mean radius open intervals. So you end up with this. Zero, 1, you have got half, you have open interval, then again you have open interval here and open interval to move here. I'll just mark like this. These are all removed. These are all removed. And then again you take the middle of this. Take the middle of this. Once again you remove. Again you remove the middle. So there will be 4 open intervals removed now at this stage. So this is the stage. This is n equal to 1, n equal to 2, and this is the stage n equal to 3. So eventually you get an and bn defined. So you have got a1, a2, a3 and so on, then b1, b2, bn, etc. So this is how it comes. So a1 equal to 1, 1 and b2 you have, so you have got a2 is equal to I21 I22 so an and so on. So you get an equal to ij n minus 1 union of that j running from 1 to 2 to the power n. 1 to n. Similarly, you have got b1 equal to a1, b2 equal to a2 and so on. So you get bn which is equal to essentially union j equal to n equal to or k equal to 1 to 2 to the power n j n. So this is your j11, j12. This is j21, j22, j23, j24. And then you have j31, j32, j33, j34, j35, j36, j37, j3. Okay, so the union of that you call Bn. Okay, now what you can easily verify or quickly compute is this from our construction, that measure of V2 is equal to 1 minus alpha by 3 minus 2 alpha by 3 square, and measure of V3 equal to 1 minus alpha by 3 minus 2 alpha by 3 square minus 2 square alpha by 3 cube, and so on. This is what you can compute. I mean, that's quite easy to verify. Okay? Right. So what you define, or if you recall, what you have defined as C alpha is the intersection of which is equal to union of this is what you have. This is the connection between the sets. Right. Now let us start defining our function Fn. Okay. So the next part of the job is definition of the function. Okay. So we define and we also immediately see that you have the telescopic property, namely V1 contains V2 contains etc. So B1 is actually shrinking. Okay, and eventually their intersection would become is called the characteristic. That's the definition. Now you define Fn equal to chi of Bn. So what does it mean? It means Fn is going to be 1 on the set Bn and 0 on its complement. On its complement is that union Ai is the complement. Okay, so on the complement the function is 0. On Bn it is equal to 1. So this is the class of functions that we define, etc. So you can actually visualize what the function is. The function F1 is 1 over here and 0 here. The function F2 is 1 over these 4 pieces, and on the complement of that it is 0. Similarly, F3 is 1 on J13, J23, J33, J43, J53, J63, J73 and J8, that is simply B3, and on the complement of that, that means the union of these open sets, the function is given to be 0, and so on. So it is defined in this way. So you get an idea of what the function is like. So what is happening to this function is that this function is becoming more and more take the value 0 on larger sets as n tends to infinity. So eventually you are left out with this C alpha. Elsewhere completely the function will be 0. Okay, so this is the one that we are getting. Now the first claim is that for that we also make some observation. What is integral of Fn is a non-negative function. Therefore, you need not put mod Fn. Mod Fn is equal to Fn. So, integral of mod Fn is the same as Fn, which is equal to measure of Bn. That's easy to see. So on Bn, it is going to be 0, and you can see what is the measure of this union of disjoint closed intervals, and the sum of the lengths of this will give you the measure. So that's it. So what is it? Measure of Bn. So you have got integral 0 to 1 this is equal to 1 minus alpha by 3 minus 2 by 3 alpha by 3 minus 2 by 3 whole square alpha by 3 minus etc. up to nth term. So you end up with minus 2 by 3 n minus 1. This is what you get. Okay? Now let me work it out. So this is the integral. That's the Riemann integral. We say every Fn is a Riemann integral. There is no problem about it. So Fn is Riemann integral, and this is what you get. Okay. Now look at this Fn minus Fn. This is equal to chi. See, I'll just a schematic diagram. So I'm taking m greater than n. So what I have is that it is a shrinking set. So you have got Bn here, Bm. This is the relation between Bm and Bn under these circumstances, shrinking. And this is 1 here, and this is 1 over here, and you are looking for the difference of that. And this is essentially the measure of this one, measure of Bn minus Bm. So you see that integral of this is going to be measure of Bn minus so you get this as equal to 1 minus alpha by 3 minus alpha by 3 into 2 by 3 minus etc. minus alpha by 3 into 2 by 3 to the power n minus 1. This minus 1 minus difference of these two. Okay, therefore you end up with the following. You can check the computation. Maybe I would have made some mistake also, but I think it's better to realize what this computation is and verify it also. Convince yourself that this is 2. So this turns out to be essentially alpha by 3, 2 by 3 whole to the power n into 1 plus n. And you know that this is less than or equal to, alpha by 3 into 2 by 3 whole to the power n into the sum, the infinite sum. If you take, because there are series of positive terms, so you get here, you get what you get will be 3. Okay, so this is equal to alpha into n, and you know that this goes to 0 as n tends to, as n tends to infinity, m also goes to infinity, because we are always taking m greater than. Okay, or more precisely, given epsilon, you can make this as small as you please, or this less than epsilon. Okay, so by choosing n sufficiently large. Okay, therefore this is a Cauchy sequence. Okay. Now we also verify one more result which we may have to use, namely, so we also claim, let's claim that we make this integral which is equal to measure of dn, which is equal to 1 minus alpha by 3 into 1 plus 2 by 3 plus 2 by 3 minus 1, and you know that this is greater than or equal to 1 minus. So this is one of the inequalities that you have. Okay, therefore integral, so the result that you get is integral 0 to 1 dx is greater than 1 minus alpha and you see that means this integral is always positive because alpha is taken to be less than 1. Okay, so this is always positive. So this is never 0. That is the point. Now we start with the solution. So we have got the Cauchy sequence, and now we assume that there is a Riemann integrable function which is the limit of this function, and then show that that assumption is false. Okay. So suppose there exists f belonging to such that limit n tending to infinity integral 0 to 1 dx equal to 0. Now we contradict this. Okay. In that case, you see that integral 0 to 1 less than or equal to x. This is the what you call second triangular inequality. Use this. This is this, and you know that this goes to 0. Okay. But what do you know about this? If you look at this, you see that this is equal to, okay, so this goes to 0. So what does this mean? This implies integral 0 to 1 mod fx dx is equal to limit n tending to infinity integral 0 to 1 dx, which we have already estimated. We estimated that this is, each one of this is greater than 1 minus alpha, therefore this is 1 minus. So you end up with this relation. If at all such an f exists, then you are going to have an inequality integral 0 to 1 is greater than 1 minus alpha. And f is related to E, and they belong to the same class. Okay? Because you see that all your fn's, the way in which fn's are defined, see this function, the limiting function, all the fn's are 0 on an. Okay? Therefore, the limit that you have is going to be 0 on the union of this. Okay? So G is taken to be 0, and you just don't know how you take it on the complement, but it's taken as a Riemann integrated function. Now let us compute this. Integral 0 to 1 to take the lower integral of gx dx. So we estimate this. We estimate this as follows by bringing in an fn in between. So what one does is this, the following. So we write this as integral 0 to 1 fx minus fnx. Bring in fn into the picture. Let us do it like this. Then you add to it integral 0 to 1. Because all these are non-negative functions, so I don't have to put an absolute sign there. Minus integral 0 to 1 dx dx. This is what I want to work on. This is the lower integral. This is the lower integral. And this, you know, is less than or equal to integral 0 to 1 mod fx dx plus, you can write, see, fn's are all Riemann integrable, therefore This is the Riemann integral is essentially the lower integral of f. So I have no, I am justified in writing this integral 0 to 1, the lower integral of I'm justified in writing this. Okay? And what you know is that Fn converges to F, that is our assumption. Therefore, this can be made arbitrarily small by choosing n large. So, given epsilon, there exists an n1 such that integral 0 to 1 fx minus less than epsilon by 2. And so also there exists n2 such that the lower integral of therefore what you end up with? You end up with integral 0 to 1 is minus the lower integral of gx dx. This is equal to 0. This is true for every n greater than n1 and n2. Or you can say that this is less than epsilon for every n greater than n, which is the maximum of input. Which implies, one more time, make it clear. The training one is therefore I don't want to jump. It's for the students. Therefore, you see that this is this integral 0 to 1 fx dx minus integral 0 to 1, the lower integral of 0. Now you see that G is defined to be 0 on the union of an. Okay, and elsewhere you don't know how it is defined. Only thing is it is taken equivalent to F. So what do you get here? What about the lower sum? See, essentially G is defined in some way on the complement of the union of an, and that is nothing but, so G is possibly not 0 on C alpha. Okay. Now compute the lower sum and the lower integral. Now here what you should observe is the following, that C alpha has no non-empty open interval within that. That means if you take an open interval containing one element of C alpha, then certainly there are elements from an coming into it. Okay. Therefore, if you work out a lower sum, then you see the infimum of f of g comes into the picture. The infimum of g is going to be 0. Okay. Therefore, you see that for that reason integral 0 to 1 gx, the is equal to 0. What does this mean? This implies integral 0 to 1. This is equal to 0. But that contradicts. So when alpha is less than 1, this contradicts. Integral 0 to 1 is greater than 1 minus alpha, which is positive. Okay? So you get a contradiction. What does this mean? Therefore, there does not exist an f such that integral 0 to 1 fn minus f goes to 0. That means the Cauchy sequence does not converge to any function in R0. That's R01 is not one. Therefore, you see that in general RAD is not complete. Now that's the proof of the theorem. Okay. So let me stop here, and I will conclude this series on Riemann integration with a short lecture, probably just indicating what all things we did to come to this conclusion. So that's my next task. Thank you very much.